Imagine stepping into an elevator on the ground floor and pressing a button for the 30th floor. The doors close. The elevator begins climbing, and within seconds, you're hundreds of feet above the ground. Now imagine something going horribly wrong. The elevator suddenly starts moving downward. The cables fail. There is nothing holding the elevator up. Would you just drop all the way to the bottom of the shafts? It sounds like the perfect setup for a nightmare. But here's the surprising part. Modern elevators are relying on one cable, one brake, or one mechanism to keep you safe. They are built with multiple layers of protection designed to control the elevator, detect dangerous movement, and stop the car if something goes wrong. There are steel cables, counterweights, mechanical brakes, speed monitoring systems, and emergency safety devices all working together. And some of these systems can stop an elevator even if the main lifting system fails. So what actually holds an elevator up? And more importantly, if the cable somehow failed, what would stop the elevator from falling? When you look inside an elevator shaft, the elevator car itself is only one part of a much larger system. Above it, you'll usually find a collection of machinery that controls its movement. The elevator car is connected to strong steel ropes that run upward through the shaft and around a large pulley called a sheave. On the other side of those ropes is something you might not expect: a counterweight. The counterweight is a large stack of heavy material that moves in the opposite direction from the elevator car. When the elevator goes up, the counterweight goes down. When the elevator goes down, the counterweight goes up. And this isn't just a clever way to save space. The counterweight is one of the most important parts of making an elevator efficient. Imagine trying to lift a very heavy elevator car using a motor. The motor would have to provide enough force to overcome nearly the entire weight of the car, plus the passengers inside. That's a lot of work. But with a counterweight, much of that weight is balanced. The counterweight is generally designed to roughly match the weight of the empty elevator car plus a portion of its typical passenger load. That means the motor doesn't have to constantly fight the full weight of the elevator. Instead, it mainly has to overcome the difference between the two sides, along with friction and other forces in the system. The ropes themselves are also not just ordinary cables. Elevators use specially engineered steel ropes designed to handle heavy loads and repeated movement. And an elevator typically uses multiple ropes rather than depending on just one. So already, we have several pieces working together. The ropes connect the elevator and counterweight. The counterweight balances much of the load. The sheave transfers the motor's movement into the ropes. And guide rails running along the shaft keep the elevator car moving vertically along a controlled path. But how does the motor actually make the elevator move? That's where the mechanism becomes even more interesting. At the top of the elevator shaft, a powerful electric motor controls the movement of the system. But the motor doesn't simply pull the elevator upward like someone pulling a rope. Instead, it turns a large wheel called a sheave. The elevator ropes pass around this wheel, and the surface of the sheave is designed to grip them. As the motor turns the sheave in one direction, the ropes move. The elevator car rises while the counterweight moves downward. Reverse the motor, and the process happens in the opposite direction. The fascinating part is that the motor doesn't necessarily need to lift the entire weight of the elevator. Remember the counterweight. Because it balances much of the elevator's weight, the motor mainly needs to overcome the difference between the two sides and control the movement. This makes the system far more efficient than simply trying to lift a huge elevator car directly. The motor can also control the elevator's speed incredibly precisely. It can accelerate smoothly when leaving a floor, maintain a controlled speed while traveling through the shaft, and then gradually slow down as it approaches the destination. This is why you usually don't feel the elevator suddenly jump upward when you press a button. The system carefully controls the motor's rotation throughout the entire journey. And while the ropes are moving, the elevator car isn't simply hanging freely inside the shaft. It is guided by rails running vertically along the walls. Guide rollers or other components attached to the elevator interact with these rails, keeping the car aligned and preventing it from swinging around inside the shaft. So the elevator is effectively part of a controlled mechanical system. The motor controls the movement. The sheave transfers that movement to the ropes. The ropes move the elevator and counterweight in opposite directions. The counterweight balances much of the load. and the guide rails keep everything traveling along the correct path. But there's still an obvious question. If the elevator depends on ropes to support its weight, what happens if something goes wrong with those ropes? After all, even the strongest mechanical component can eventually wear out or fail. And this is where elevator safety becomes much more interesting. Because elevators are designed around the assumption that nothing will ever break. They're designed around the assumption that something eventually might. This is why elevators don't rely on a single rope. Instead, elevator cars are typically suspended using multiple steel ropes, all working together to support the load. These ropes are specifically engineered for elevators and designed to withstand enormous forces and repeated cycles of movement. The idea is simple: don't make one component responsible for everything. If one rope develops a problem, the others can continue supporting the elevator while the system is taken out of service and inspected. But the ropes are only one layer of protection. Elevators are also regularly inspected and maintained, because even extremely strong steel ropes experience wear over time. Technicians look for signs of damage, corrosion, deformation, and other problems that could compromise the system. So the first line of defense is preventing a rope failure from happening in the first place. But engineers don't stop there. They also plan for a much more serious possibility. What if the elevator car somehow begins moving downward faster than it should? At that point, the elevator needs to be able to stop itself. And this is where one of the most important safety systems in an elevator comes into play. It's called the safety gear. The safety gear is a mechanical braking system attached to the elevator car. If the car begins descending at an unsafe speed, the system can activate and grip the fixed guide rails running along the shaft. Instead of allowing the elevator to continue accelerating downward, the safety gear creates a powerful mechanical resistance against the rails. The elevator slows down and can be brought to a stop. But how does the elevator know that it's moving too fast? It doesn't depend entirely on the motor. It doesn't wait for a human to notice. And it doesn't need someone watching from the outside. There's another mechanical system specifically designed to monitor the elevator's speed. It's called the overspeed governor. And this is where the elevator's safety system becomes especially clever. The overspeed governor is essentially the elevator's mechanical speed watchdog. Its job is to monitor how quickly the elevator car is moving. Normally, the governor rotates as the elevator travels up and down the shaft. As long as the elevator is moving within its normal speed range, nothing unusual happens. But if the elevator begins moving too quickly, the governor is designed to react. Once the elevator reaches a predetermined overspeed condition, the governor activates a mechanism that can trigger the elevator's safety gear. That safety gear then grips the guide rails. The important thing is that this system doesn't need to wait until the elevator reaches the bottom of the shaft. It is designed to detect excessive speed while the elevator is still traveling. Think about what that means. The elevator isn't depending on the motor to save it. It's not depending on the ropes to remain perfect forever. And it's not waiting for the elevator to hit something at the bottom. Instead, there's an independent system whose specific purpose is to detect dangerous speed and activate a mechanical stopping system. The safety gear can then clamp onto the guide rails and convert the elevator's downward motion into friction and deformation that slows the car. Exactly how the mechanism works depends on the elevator design, but the basic principle is the same. The elevator moves along the rails. The governor monitors its speed. If the speed becomes excessive, the governor triggers the safety mechanism. The safety gear grips the rails, and the elevator is brought under control. This is one of the reasons the idea of an elevator simply falling freely down the shaft is so misleading. A real elevator has several systems between something went wrong and the car reaches the bottom. But engineers don't stop there. There is another layer of protection waiting at the very bottom of the shaft. And it's designed for a very different purpose. They're called buffers. At the very bottom of an elevator shaft, you'll find another safety feature that most passengers never see. They're called buffers. Their job is to absorb energy if the elevator car or counterweight travels beyond its normal stopping position. Think of them as the final layer of protection at the bottom of the shaft. Depending on the elevator design, buffers can use different technologies. Some use heavy-duty springs. Others use hydraulic systems that absorb energy as the elevator moves into them. A hydraulic buffer works somewhat like a shock absorber. If the elevator reaches the bottom at an abnormal speed, the buffer is designed to absorb some of that motion and reduce the forces involved. But there's an important distinction. The buffers are what normally stop an elevator. The elevator is supposed to stop using its normal braking and control systems. The safety gear and guide rails provide another layer of protection if the car moves too quickly. The buffers are there as an additional safeguard if the elevator travels farther than it should. And this pattern keeps appearing throughout elevator engineering. There isn't one magical device that makes an elevator safe. Instead, there are layers. The ropes support the elevator. The counterweight balances much of it. The motor controls movement. The normal brakes hold the elevator when it's stopped. The governor monitors speed. The safety gear can grip the rails. And the buffers provide another layer of protection at the bottom of the shaft. But there's another situation that happens much more often than a cable failure. A power outage. If the electricity suddenly disappears while you're inside an elevator, the motor stops. So what keeps the elevator from simply dropping? The answer is another safety feature that's much simpler than the systems we've been talking about. Mechanical brakes. When an elevator is stopped at a floor, it isn't being held there only because the motor is running. In fact, the motor can stop completely. Mechanical brakes can hold the elevator in position even when there is no power driving the motor. This is important because electricity isn't guaranteed. A building can lose power. A circuit can fail. A component can shut down. The elevator's safety systems have to assume that these things can happen. The braking system is designed so that when the elevator isn't being actively driven, the brakes can hold it in place. So if the power suddenly goes out, the elevator doesn't simply become a free-falling box. The motor stops providing movement, but the mechanical braking system can keep the elevator from moving normally. Many elevators also have emergency systems that can provide lighting and communication inside the car. Depending on the building and elevator system, backup power can also allow certain controlled operations during an outage. Some systems can move an elevator to a suitable floor under specific conditions, allowing passengers to exit safely. The exact behavior depends on the elevator's design and the building's safety systems. But the important principle is the same. A power failure doesn't automatically mean the elevator loses all control. The elevator has mechanical systems that don't depend on the motor actively pushing it upward. And there's another safety feature that passengers interact with every single time they use an elevator. The doors. It might seem obvious that an elevator door should only open when the elevator is actually at a floor. But think about what would happen if the doors could open at any point in the shaft. You could press the open button while the elevator was between floors and potentially step straight into an empty shaft. So elevators use door interlocks designed to prevent that from happening. The doors are connected to safety systems that verify the elevator is in the correct position before allowing the doors to open. This means the doors aren't just there to keep passengers inside. They're also part of the elevator's safety system. And once again, we're seeing the same principle. Elevator safety isn't based on one device. It's built from layers of systems that are designed to prevent different kinds of failures. So, could an elevator actually freefall all the way to the bottom? In an ordinary modern elevator, that scenario is extraordinarily unlikely. And the reason isn't that elevator cables are somehow impossible to break. It's that the elevator is designed with multiple layers of protection between a failure and a dangerous fall. The ropes are engineered to carry the load and are used in multiples. The counterweight balances much of the system. The motor and normal braking system control the elevator's movement. The overspeed governor continuously monitors the elevator's speed. If the elevator moves too quickly, the safety gear can activate and grip the guide rails. And if the car travels farther than it should, buffers at the bottom of the shaft provide another layer of protection. Even the doors have their own safety mechanisms. Each part is solving a different problem. That's the key idea. Engineers don't design the elevator by asking, "What if everything works perfectly?" They ask a much more useful question. What happens if something doesn't? That way, a single failure doesn't automatically become a disaster. And that's why the classic movie scene of an elevator cable snapping and the entire car immediately plunging dozens of floors isn't a good representation of how modern elevator safety works. The real engineering is much less dramatic and much more clever. Instead of trust in one component, elevators use redundancy, monitoring, mechanical brakes, controlled movement, and multiple independent safety features. The goal isn't to make failure impossible. The goal is to make a dangerous chain of failures extremely difficult to complete. And every time you step into an elevator, you're relying on that philosophy. Think about what happens the next time you step into an elevator. You press a button, the doors close, and the car begins moving. It feels simple. But behind that simple ride is an entire system designed around one idea: control what happens when something goes wrong. The ropes carry the elevator. The counterweight balances much of the load. The motor controls the movement. The brakes hold the car when it needs to stop. The governor watches the elevator's speed. The safety gear can grip the guide rails if the car moves too quickly. The buffers provide another layer of protection at the bottom of the shaft. And the door interlocks help prevent the doors from opening when the elevator isn't safely positioned. None of these systems has to do everything by itself. That's what makes elevators so reliable. They're not safe because one component is indestructible. They're safe because the entire machine has been designed with failure in mind. So the next time you're standing inside an elevator several floors above the ground, remember what's actually happening around you. You're not simply sitting inside a box hanging from a cable. You're inside a carefully engineered machine with layers of mechanical and electronic systems constantly controlling its movement and protecting its passengers. And perhaps the most impressive part is that you barely notice any of it. You just press a button, the doors close, and a few seconds later, you're exactly where you wanted to go. That quiet, uneventful ride is the result of decades of engineering designed to make sure that when something goes wrong, the elevator has more than one way to keep you safe.